Good morning, everyone. Let's begin lecture. We have a bunch of scantrons left over for those of you that were mysteriously not here on Tuesday or that we didn't get to. And I've got those. I don't have them with me today, but I'll probably have them Tuesday. Alternatively, you may come to pick it up, the printout from me at office hours, informal office hours today, about 1:30 in room 158 in the Physical Sciences building. That's my regular office, and it's like I got scantrons everywhere and printouts and stuff, so it's kind of messy, but I'll dig yours out if you still need it. So come by, and I'll probably be leaving there at about 3, so you can take your time. We're going to try to have a full lecture. Get your clickers ready. We got clicking to do. You have some explaining to do. And we all got some interacting to do. Last time we talked about the Nardo Ring as a way of introducing the idea of uniform circular motion. And uniform circular motion is an ideal case or an idealized state of motion that Sir Isaac Newton leveraged when he was developing his theory of universal gravitation. We will get to that today. We're going to get to a whole bunch of stuff. So we're cleaning up chapter 3 and diving headfirst now into chapter 4. And I made some more highlights this morning in the text. So hopefully you're able to get highlights viewable on the bookshelf application. So just in way of review, some of the things that we talked about, the whole idea of this imaginary circle that's tangent to the actual physical path, you kind of visualize it and say to yourself that for at least a short distance, that imaginary circle is right on the path. And even though the path is not a perfect circle, for an infinitesimally close, let me get my cursor over here, for an infinitesimally close or infinitesimally small neighborhood, it's pretty good. It's a pretty good approximation. That's what the math department would say, infinitesimally close or infinitesimally small. But for us guys, in the physics department and engineering, the colloquialism they use, instead of that phrase, they say, well, it's good enough for government work, close enough for government work. Okay, so the path may not be a circle, but we can approximate it, and that's close enough for government work. Now let's take a look at some of the other factors here. The radius from the center of that circle out to the actual point on the path, that circle, that's the particular radius that's useful for us. There's an infinity of radii, but that particular one can also be used as a position vector. I've got it written in blue as a blue line segment, but yeah, you can think of it as a vector pointing from the center of the circle to the point on the path. That is also a point on the circle. And so it is expressible as a vector, a location vector. It's perpendicular to the velocity. Here's the symbol that we frequently use, R with a little arrow over the top of it, or boldface R. By the way, I was looking you know what I was doing? I was reading the textbook, or I was listening to it, I should say. I was having the textbook read itself. I wasn't reading, the textbook was reading itself. And I actually kind of like it, but it blows some of the equations. It tries to tackle the equations, can't do it. Another thing is and this is the publisher, made an error. Some of the equations are supposed to be vector equations in boldface, and they're not. So just a word of caution on that. Anyways, this perpendicularity concept is something that we need to really focus on, and we're just going to re-emphasize it here. Now, that velocity vector, as always, is tangent to the path, no matter what the path is. And if it's a curved path, there's a radius vector perpendicular to the velocity. And because that is true, one of the things that we found out was that the acceleration on uniform circular motion is perpendicular to the velocity, because there's no speed up and no slow down. That's another thing that we talked about for uniform circular motion. So that acceleration vector, you go ahead and trace it in lightly. I made it blue, and it's pointing toward the center. Now the red position vector R was pointing outward to that red square that's on the circle and on the path, the common point between the path and the circle. But this vector points from that object on the path towards the center of curvature. It's an important distinction because for us, and here's the symbol for it, for us, the directionality of that acceleration is pretty important. Matter of fact, the directionality of the net force is in the same direction as the acceleration. And so we call the acceleration and the net force centripetal. And so that's why the perpendicularity is important. It's a pretty important vocabulary term for us. Now let me break it down for you in terms of root words. Centripetal, C-E-N-T-R-I-P-E-T-A-L. Okay, century means center. P-E-T-A-L means to come or to approach something. So it's heading towards, it's an arrow that heads toward the center. Now another word that you can write down in your notebook is something that you've probably heard used from time to time, and that is centrifugal. C-E-N-T-R-I-F-U-G-A-L. Centrifugal. Okay, so write that one down carefully. Right below that in your notes. C-E-N-T-R-I-F-U-G-A-L. Okay, now that you've got it written down, cross it out, because we never use that in this class. That is a concept that we're not going to use. Centrifugal is related to center, century, C-N-T-R-I, but fugal, fugitive. What do fugitives do? They flee. So centrifugal means away from the center. And our acceleration, no way, Jose. Our acceleration, our net force, are not away from the center. They're toward the center. So we're going to use centripetal. We're never going to use centrifugal. Now, if you're building a centrifuge, okay, you can use it as an adjective, but we're not going to be messing with that. Okay, so make sure to cross that out, and do not misunderestimate the importance of this term, centripetal. Okay, now, we also talked about the Nardo Ring. And just to review this, it is a circular test track in the south of Italy, down in the boot heel. And it was built a number of years ago for testing automobiles. Basically, endurance runs to see how long their machines would go before they break down or boil over or whatnot. The outer ring is designed for an optimal speed of 149 miles per hour. And that is with the steering wheel straight. And so that is for something like race cars, and the Italians, Ferraris, those are some of the best race cars there are. Okay, so now if you want to go faster than that, you got to put some torque on your steering wheel or go to a different part of the track. Actually, that's the fastest you can go on that track with your steering wheel straight. Now, the innermost lane, as I mentioned before, is for testing stuff like trucks. I guess passenger cars that aren't supposed to go much more than 50. So that's the optimal speed. It's a little bit smaller and it's not banked as much. But at 50 miles an hour, approximately, you just keep the steering wheel straight and you don't have to, you're still going to be on the steering wheel. I mean, they're not going to have a situation where there's no test drivers, but the Nardo Ring is a great example, a physical example of a pretty close to perfect circle for things that move, for everyday things that move in a perfect circle and frequently with uniform circular motion. Okay. Now we're going to derive some equations on the simple circular path at constant speed, i.e. uniform circular motion, and I want you to sketch your diagrams really carefully. Now what we're going to do, we're going to look at kind of a diagram, a schematic diagram like this, at two different instants of time. So here's the instant of time called T1. All right? And at time T1, your position vector R is straight to the right. And the center is right at the center of the circle. Okay? And then your velocity vector, we're going to say that this thing's going anti-clockwise. And so the velocity vector at that point only is straight up. All right, so make it right angles, of course, and because it's a circle, it has to be straight up, 90 degrees away from your position vector R. Now, at a slightly later point in time, a little bit further down the track at the Nardo Ring, at time T2, all right, we're going to say that you're 30 degrees further along. So your R vector here is a little bit different position, and V, your velocity vector up here, it's still magnitude V because we're at uniform circular motion. So this is like going at 149 miles an hour, say, on the outer ring. But your tilt angle here for V is also 30 degrees anti-clockwise. Okay, 30 degrees to the left. Okay, the position vector has swept out 30 degrees. And so since the velocity vector is always perpendicular to that, that also moves out 30 degrees in an anti-clockwise manner. So here are your two instances. So this is like snapshots at two different times, different instants of time, not too far apart, a few seconds apart, T1 and T2. All right, now what we're going to do, make sure you have a good size diagram of this, and what we're going to do is kind of analyze this and break it apart. And then we're going to put together different parts and see what we can see. That's called analysis, breaking stuff together and then putting it together is synthesis. So what we're going to do is kind of copy, we're going to make a triangle, an isosceles triangle, out of these two position vectors. Okay, so I'm going to ease my triangle, there it is, and I'm just going to park it down here. Okay, so this is tail to tail. Now I'm not putting any arrowheads on this. I will on the velocity though. All right. Now I've got two velocity vectors, one straight up and one kind of tilted to the left a little bit, kind of northwest-ish by 30 degrees. And we're going to, okay, now watch. Eyeballs. Here we go. There's the copy. All right, and I'm going to park that up here to the upper right. All right, just so we have stuff, you know, kind of. So these are my two sub-diagrams. All right, now I've broken the things, the snapshots apart, and now I've reassembled, I've synthesized two new triangles. This triangle down here in black is the position triangle, and this one up here in red is the velocity triangle. So make a note of that in your sketch, just so you can remember, which triangle that I'm talking about. All right, so let me make it a little bit bigger. Here we go. Do you have a question? Okay, good. All right. All right, so here's my velocity triangle down here in the lower left, and I just made them a little bit bigger. And I put here's my two snapshots. I still got those. They're up in the corner. You still have them in your notes, so that's good. And now what we're going to do is connect the dots down here on the position triangle. So we're going to form a base right here, and that's going to form an isosceles triangle. And I call it isosceles, my wonderful students, because the sides are both length r. So whatever, I forgot to look up the radius of the Nardo ring. But whatever the radius of the Nardo ring, 300 meters or whatever it happens to be, it'd be 300 and 300 on this triangle. All right. Now, that base of the isosceles triangle is the approximate distance that you travel. Now, it's not the exact distance because you're on a curved path. And this is a straight line segment, but it is fairly close. So if the curved path is if the curved path is 111 meters, this straight line segment might be 109 meters. Okay, so they're going to be pretty close together. Now let's do the same thing for the velocity triangle. Connect the arrowheads of the two velocity vectors. Now they're copied tail to tail, same as the position vectors down here. Although these position vectors don't have arrowheads. That's all right. We'll work with it. And here's the base. And it's kind of upside down, but it's still an isosceles triangle because I have V and V. Question? The bottom is the position triangle. The top one up here in the upper right is the velocity triangle. And the way you can know that, what is your name again? Cassidy. The way you can know that, Cassidy Meister, is position, R. R and R. And then V's for velocities. Okay? Now, what is this thing going to... mental IQ test question here. What should we call that red dotted line segment? That red dashed line segment. What should we call that? Raise your hand. What should we call that? Think. It's not a velocity. It's made with a pair of velocities. So what is that? Approximate change in direction? No. These are velocities. Care to revise your answer? What do you think? Is it what? The student up here in the front, Tanisha, said, is it like V2 minus V1? And the answer is yes. That is delta V. All right? Now that one we're just going to leave as a line segment too. It would be from V1 to V2, but we're just going to be working with the magnitude, so the direction of that particular arrow is not needed in this derivation. Now, a couple things about this. If you remember from geometry class in high school, these two triangles are going to be similar. Now, the angles are equal, but the sides are not equal. You can't really say that a number of meters in the position triangle is equal to a number of meters per second, Austin, in the velocity triangle. But you can say that they're proportional, okay? They have the same ratio and stuff, and that ratio is what we are hunting for, okay? Now, I've already made this clear. Go ahead and make a note that that approximate distance is very close to V delta T, right? You know, distance is speed times time, right? So if you have an instant of time, Tanisha, T2 minus T1 for delta T, you know, and a speed V, this is the distance, okay? And so, but it is approximate because it's not on the actual path. It's kind of cutting the corner of the curved path. All right, now let's set up the proportion. All right, and what we're going to do is set up a proportion is a pair of ratios. And so what we're going to do is a ratio between the long side of the position and the long side of the velocity triangles, and then the base of the position and the base of the velocity triangles. So here it is. All right, R over V, there's your first ratio. And if this pair of triangles is proportional, then that will be equal to the base of the isosceles position triangle, that's V delta T, and then over delta V, which is the base of the velocity triangle. All right? And so now, I want you to look at that proportion. Now, this is Math 101, or this is like Algebra 2 class. We haven't done any physics yet. But do you see anything in there that strikes your fancy, that looks reminiscent of anything? What do you see? Ding, 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 ding. The change in velocity over change in time is an acceleration. We don't have that. We've got the flip-flop of that. So if we take this proportion and flip-flop it, we'll have an acceleration in there. See it right here? This is delta T over delta V. That's not bad. If we flip-flop it, that'll be the acceleration. And that is what we're trying to figure out here. All right, so here we go. This is the, and go ahead and make a note, this is the key proportion that locks in all the centripetal acceleration formulas. You haven't done any physics yet. You've just figured out a proportion. But now with this key insight from, what is your name again? Canna. From Canna up here in the fourth, Canna. I can't say it right. I'll try to say it again. Hannah. Okay, Hannah in the third row has given us the insight. And just to reinforce, here's the isosceles sides. Position dot speed, and then over here, here's the isosceles base, position dot speed. So position triangle over speed triangle, velocity triangle. Okay, and what we're going to do now is, here's the flip-flop. Okay, so we flip-flopped it, and now we got that nice delta V over delta T. And I've parked this V. Now this V over here, I don't want it touching my acceleration. So I'm going to cross multiply it over here. So this would be up here, R over V squared, if I cross multiply that V, which is kosher. You can do that. And then flip-flop it, it becomes V squared over R over here. All right? And that, my wonderful students, is the formula for centripetal acceleration. A equals V squared over R. And you could tell your parents tonight, or your BOSS at work, yeah, we were doing some calculus today. And we just went through a nifty little calculus, visual calculus derivation, that the math department would be jealous if they could see how we did it. Anyways, it's a calculus result. And that is our formula for the centripetal acceleration. That tells us the number of meters per second squared you're being pulled toward the center in the centripetal acceleration. And it's because of proportional triangles. So make a note. Because we have proportional triangles, the speed triangle and the position triangle, we can say that the centripetal acceleration is V squared over R. And the centripetal force is simply F equals ma of that. So F subscript C is m times v squared over r. Okay? And those are the two centripetal formula forces. So anytime you have something moving on a circular path, like if you have something that you're swinging around, like what cowboys do, you know, with a what do they call that? A lasso, you know, and you're at the rodeo and you're you know, roping stuff. Centripetal acceleration city on something like that, provided by the cowboy. You know, he's swinging it. He's continually providing some newtons of pull force towards himself, and it swings around him, or around, you know, whatever the, you know, the center of motion is. All right, so those are my two formulas. Now I'm going to keep going. I want to talk about some famous examples, and we're about to start doing some clicking here. We're going to talk about Sir Isaac Newton. He's the one that figured out centripetal acceleration and centripetal force, and then he used it to figure out universal gravitation. So here we go. This is Sir Isaac Newton. The master stroke of Sir Isaac Newton is his law of universal gravitation. Now, at the time, he had decent measurements for terrestrial acceleration. You know, in other words, the legendary apple from the apple tree. Using distances and times, they knew it was it was, I guess they probably would have used inches and seconds. And I think it's 32 feet per second squared. But what we would say is it's 9.8 meters per second squared. He could also estimate the moon's centripetal acceleration because he had fairly good estimates of the distance of the moon, and of course everybody knows how long it takes to orbit. So he knew the distance from to our moon as a multiple of Earth's diameter, and that was sufficient for him to make his conjecture about universal gravitation. Okay, because the Earth's diameter was known. So he was able to put together that distance information and then this time information, 27.3 days for one lap around the Earth. The moon's orbit is not a perfect circle, but it's pretty close. And if I mapped out the exact shape of the moon's orbit and a perfect circle of the same size, you would not be able to tell them apart. So he was thinking in terms of, okay, circular motion for the moon, centripetal acceleration. Is it related to my apple tree acceleration, my apple falling from the apple tree acceleration? Now, before we get to that concept and put it all together, I want to ask you, whoa, excuse me. My microphone fell off. Okay, I want to ask you an easy clicker question. All right? So get your clicker out and get your brain out. And I'm going to give you a very short amount of time to make this decision, like 30 seconds. Okay, now if you're operating your clicker for the first time, hold the power button down. We are on frequency BB. Hold the power button down until the square flashes, then type B and B, and you'll be ready to go. Now, hopefully this is an easy one, and do not let these two ferocious hound dogs intimidate you. Go ahead and answer this question. And just so you know, I use all these images from Reddit and stuff because some questions, you know, they don't need a diagram, but again, they can't be just regular text, so I just put something nice in from Reddit. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys. A bunch of geniuses, 99%. Only 2 people answered 120. Yes, 60 squared, 60 times 60. So, all right, so let's go back to gravitation and talk some more about his great achievement. All right, now Newton conjectured that the same force that pulls the apple down towards the ground or towards his coconut and hits him on the coconut is the same force that pulls the moon towards the center of the earth, a centripetal force that keeps it on its circular orbit. In other words, he assumed that the moon is on a free fall accelerated path. He was able to, and that is accurate. That is a correct assumption. It really is in free fall. But it's moving so fast it never, crashes to Earth. It just keeps, the Earth curves away from it at the same rate that it curves towards you. So it just assumes a nice circular orbit. And he was able to estimate, knowing the size of Earth, knowing the length of the lunar month, that the centripetal acceleration was about 0.027 meters per second. Now, compared to G here on Earth, like here in Orlando, 9.8, that's about 1/3600th of G. So in other words, the acceleration, he was trying to figure out, all right, I've got this acceleration in Cambridge for this apple tree, the apple falling from the apple tree, 9.8 meters per second squared. And okay, according to my calculation, the moon's got about a 3600th of that. So he's saying to himself, not to you, but to himself, how do I make sense of that? And the thing is, he knew that the radius of Earth was 1/60th of the distance to the moon. So center to center, from the center of the Earth to, for instance, Orlando, or in this diagram, from the center of the Earth to like Cape Town, Africa, that distance is 1/60th of the distance from the center of Earth to the moon. Now, he knew that as well. And so the question is, all right, my accelerations have a ratio of about 3,600 to 1, and my distance ratio is about 1 to 60. And 60 is, if you square 60, you get 3,600. So his mind was probably thinking like this. Is this a coincidence, or is it indicative of a law of physics? And here's another way to look at it. Here's a diagram to scale. If you could actually go out in space and look back at the Earth and the moon, these are the true proportions. Try to draw this. Here's the Earth down here in the lower left corner of the screen, and way up here, this little teeny circle up here, that's the moon. Now, that is a legitimate scale for the size of each. There really are that size relative to each other, and for distance. Now, in most textbooks, they always make the Earth right here and the moon like 2 inches away so that it fits on the page. But in reality, these are the true proportions. Okay, so the distance ratio is 60 to 1. And the acceleration ratio, actually, if the distance from the surface of the Earth to the center of the Earth is 1 unit of distance, then the distance to the moon from the center of the Earth, it actually works out to 60.3. So it's pretty close to 60. And the acceleration, if you have 1 unit of acceleration, 1 g, at the surface of Earth, then the acceleration over here would be 1 over 3599.6. So that, again, is pretty close to 3,600 in the denominator there. So that's a small fraction of the actual acceleration. And just to reinforce, that's about 1 over 60 squared. And so Sir Isaac Newton probably thought, does the force of gravity that produces this centripetal acceleration, does it depend on 1 over the square of the distance? Because that's what he's looking at here. That the acceleration is 1 over 60 squared, and the distance is 60 times, for the moon. So there's your conjecture. And Sir Isaac Newton said, no, my wonderful students. Let's see, who would have been his student? Edmund Halley, the famous astronomer. That was actually a friend of his. Discovered Halley's comet. Here's what Sir Isaac Newton said. My wonderful student Edmund Halley and all England. Universal gravitation is universal. And it depends on only two physical factors. One factor being the mass of each object. Which is cool because we know that the interaction of the skateboarders depends on the mass of each guy. The speeds that they attain. All right, so this is not too unusual. And he said, okay, that force depends on the distance apart. And it's going to be the square of the distance, and it's going to be in the denominator. All right, so basically, he said it has to have this property. If you have more mass, you're going to have more force, a bigger pull force. All right, now, he did not know the mass of the Earth or the mass of the moon, but he figured out this law, and after him, they were able to figure out the mass of the Earth because of his formula. He also said if you have more distance, the force is going to get weaker. All right? And that's what we find. The acceleration due to gravity of Earth at the surface of Earth is 9.8, but way out there at the moon, it's only 0.027 meters per second squared. So it's pretty diluted. All right. Now here's the formula that he came up with. A constant G, known as Newton's constant or the gravitational constant, times the product M1, M2, the product of the two masses. So for Carl and Bob, it would be 40 kilograms times 80 kilograms for those two guys. Okay? And then down in the denominator, the square of the distance between the two objects. And that is the Newton gravitational law. Now, what is the constant G? The constant G is a number. You can look it up on the internets. It is a conversion constant. At least it started out as a conversion constant. Kind of like when you're converting from Fahrenheit to Celsius, you have to either multiply by 9/5 or multiply by 5/9. And that's kind of what you got here, because two mass measurements, m squared over a distance squared, is not a Newton. You want kilogram meter squared per second, you want kilogram meter per second squared, and capital G gets that conversion for you. So it converts from a pair of mass measurements and a square of a distance measurement and converts it into Newtons. And this form of the force law for universal gravitation is very well verified. Matter of fact, the guy that really put the total lockdown on it was Edmund Halley, H-A-L-L-E-Y. I might put a blurb up for reading about Edmund Halley and Newton in web courses for your homework tonight, this weekend. Edmund Halley predicted that, all right, if this law is true, then I think it applies to the orbits of ellipses. And they knew, the orbit of comets. They knew that the orbit of comets were elliptical, very eccentric, very wide, very oblong ellipses. And he went back in the historical record and he said, well, there's a comet in this year, a comet about 76 years later, and another comet about 76 years after that. And he said, I think that's the same comet, and it comes back on its elliptical orbit every 76 years or so. So he predicted it, for the end of, I think it was 1725. the year that he predicted that that comet would reappear, and by God, it did. Right on the money. 1705 or 1725, I think. Now, he was dead at the time, and I believe Sir Isaac Newton was also dead at the time. But it was this huge, right at Christmas time, the end of that year is what he predicted, and at Christmas time it was there, and it's known as Halley's Comet, and we've observed it many times since then. And it was a total verification of Sir Isaac Newton's law of universal gravitation. This is probably the most famous equation of Sir Isaac Newton. Now, we're going to use that equation and see what it means for stuff like spacecraft orbiting Earth, because NASA also uses it, and NASA has used that equation, the law of universal gravitation, and a lot of big computers to put men on the moon. And so they know what they're doing, and you can consider men on the moon and coming back from the moon to be a huge verification, just like Halley's Comet. Now, let's talk about the moon and a spacecraft. So we've got the spacecraft out here at some distance r, and here's the center of the Earth down here in the lower left corner, okay? And here's the distance, or the position arrow in blue. And we're going to say, all right, Earth's got a mass. We'll give that a symbol, capital M. And the spacecraft is going to have a mass. We'll give that lowercase m with a subscript s for spacecraft. And if you want to know the actual tonnage of the Earth, it's 6 times 10 to the 24 kilograms. So that's a lot of kilograms. And a spacecraft is going to be pretty teeny compared to that, just as you are pretty teeny. In fact, this entire room is pretty teeny. The entire city of Orlando is teeny compared to 6 times 10 to the 24 kilograms. Now, don't worry about memorizing that, but if you want to know, that's what it is. You can look it up on the NASA website. Now, let's take a look at some examples of what this equation can do for us. All right. For example, you know, you have a satellite. NASA's trying to figure out how to put it in orbit. And they have to use rockets. They want to put it a certain distance from Earth to accomplish whatever mission it's supposed to do. All right? And have your clickers ready, because we got some clicking coming up. I think you can go to the, I think you can. All right. You don't want, I don't want to risk any accidents or anything. Okay. God, that's going to be on the transcript. I didn't mention your name, man. Okay, good. So what was I talking about here? Okay. Yeah, so NASA, you know, they're trying to put a spacecraft, and they put them at different orbits. You know, like the space shuttle's up at a certain orbit, and the space station, I think, is a little bit higher than that. And Hubble Space Telescope is a little higher than that. And they have different orbits. Some of them are way out there, and the microphone, it fell off again. All right, here we go. Whoa. All right. So they're putting it up there at a certain distance, but they have to use the right size rocket. If they try to get it up there, you know, to the space shuttle, and their rocket's not big enough, it's going to come back and crash into the ocean or something. All right. Now, here is the key for us, Victoria. If you're down there at Mission Control and you're trying to figure out an orbit, a lot of times they'll put something on a circular orbit. It's good. Sometimes they want an elliptical. We can handle that. But we're going to do circular orbits. Okay. Now, if it's circular, you can use the centripetal force formula very nicely. Here they are. Okay. On the left is the gravitational force formula. And on the right is the centripetal force formula. Now, that centripetal force formula is not essentially part of gravitation. In other words, it can hold for anything on a tabletop, a horizontal tabletop moving in a circle, just as well. So there's nothing essentially gravitational, but because gravity does allow you to have a circular orbit, you can use it with gravity. All right, here we are. G equals m, capital M times m subscript s divided by r squared. And on the right side, m subscript s, the mass of the spacecraft, times its centripetal acceleration. So this is the centripetal acceleration it needs to stay on this orbit of size r. So r is the orbital radius. All right. Now, cancel the factor of ms from both sides. The mass of the spacecraft is on both sides, and therefore you can cancel it out. Okay? So just burn those babies out, and let's simplify it a little bit. Here's the leftovers. Capital G times capital M in the numerator on the left, divided by r squared in the denominator on the left. And then on the right side, it's just v squared over r now. And hey, you guys, this is the acceleration. And the technical term for this is the gravitational field strength. And this is v squared over r, okay, centripetal acceleration. So now we've got an equation about accelerations. Now we're going to mess around with it a little bit more. And we're going to get these r's out of the way, all right? Or we're going to simplify the r's, all right? And so if you, oops, I got that CC in the way there. Let me go to the next. There it is. Okay. So there's your total cleanup. Capital G, capital M in the numerator on the left, divided by r in the denominator on the left. And that's equal to v squared. Now, what that means is if you know the radius or you know the speed, if you know the radius, you can figure out the speed you need. And that'll help you build the rockets of the right size. If you know the speed you need, you can figure out how high you have to park it. And that also controls, or that also determines the size of the rockets that you need. So NASA has, half, as they say, half the PhDs on the planet messing around with this and other equations like it. Now, if you know the radius of the orbit that you want, you can figure out the required speed, v, and then design your rockets appropriately. Now, when would we want to do something? When would we want to control the altitude, the radius of the orbit, how high it is above the Earth? Well, for instance, you want to have a satellite that's low enough to keep an eye on the Russians and what they're doing. You want to read their license plates. You want to read the credit card number in their wallet is what you really want to do. So you got to have a satellite. It can't be way out there. We have good telescopes, but you still have to have them in fairly close. All right, so this is the kind of thing that you do if you want to design the orbit of a spy satellite. Or any other satellite that's looking down, like a weather satellite. You have a certain kind of telescope or radar operating from space, and from tests on Earth that it's got to be a certain distance away from the surface or from what it's observing in order to get good observations. So you use this equation for that. Here's another example. If you need a certain orbital speed, okay, so you want you want it passing overhead at a certain speed, for instance, or you want it to move, in any case, along its circular orbit at a certain speed. Okay, yeah, we can do that. But that, if you know the speed, it determines r, the altitude, or the distance from the center of the Earth, and in that, it also controls the altitude, the distance above the surface of the Earth. All right, now what kind of satellite? Well, we have a set of satellites, Buku satellites, B-E-A-U-C-O-U-P-S, Buku satellites, that orbit the Earth fast enough that they orbit exactly once per day. So they're at just the right orbit out there that they have a speed that takes them on that orbit around Earth once per day. Anybody know what those satellites are called? What do they do? Anybody have an idea? Mental IQ test question. You know, you guys use them every day. These are what we call geosynchronous satellites. Anytime you call long distance, well, frequently when you're calling long distance, you're on a satellite. You ever talk with somebody and it takes a second or two for them to respond? You know, I was talking to somebody in the Philippines about a track phone yesterday. And it took a second for their response to come through because they're bouncing off a satellite in geosynchronous orbit. And the way that works is because the Earth spins once per day and that satellite orbits once per day, it seems to be, it's moving, but it never seems to be any place else but right up there, you know, over Brazil or over Peru or wherever it is, you know, over the equator. And that's why your satellite dishes, you know, so if you have DirecTV, that's another geosynchronous satellite. You know, you turn your satellite dish towards the DirecTV satellite, and you got TV. So that's an example of using Sir Isaac Newton's law of universal gravitation and the centripetal force formula. The whole idea of centripetal force and centripetal acceleration. Gm over r equals v squared. Let me pause for questions. Yes? Capital M is Earth's mass. And it's interesting here, thank you for pointing that out, the mass of the spacecraft doesn't matter. So any size spacecraft that you want on geosynchronous orbit, they're all at the same altitude. You know, whether it's the size of a bus or the size of a basketball, you know, or anywhere in between. If you can get it up there, it'll be up there on geosynchronous orbit. Another question. Okay, let's keep going. I want to talk about the astronaut in this picture pushing off a spacecraft. So this is some guy, actually, it's somebody out in space wearing a spacesuit, and they're messing around with a really tiny satellite that looks like a satellite, but most satellites they put in space are about 4 or 5 times bigger than that. But for this picture, it's good. Now, Newton's third law, if the astronaut pushes on the spacecraft will push back on him if it's rigid, right? And those two forces are listed with the letter capital F. So we're going to talk about that. Another thing, in addition to the interaction forces being the same, the contact time is the same. So delta T, you know, so if they're in if he's pushing for 1/10 of a second, well, that's the interaction time. Now, because that is true, the product of F and delta T for both spacecraft and astronaut has to be the same. Now, in vector terms, it would look like this. Here's the force on the human times the interaction time. And here's the force on the spacecraft times the interaction time. Now the forces are equal, but oppositely directed. And that minus sign here means that the force on the human is opposite, minus sign, in direction the force on the spacecraft. So if the spacecraft gets some newtons to the right, the force FH on the human is off to the left. And so if you have equals times equals, that's got to be equal, right? And so this particular thing is true. Now, the force on the human, that's F equals ma. So let's put that in. All right, here's F equals ma for the human, the mass of the human times his acceleration. And we know that if their masses are not the same, just like with Carl and Bob, that they're not going to have the same accelerations. All right? Same thing over here. Here's F equals ma for the spacecraft, the mass of the spacecraft times the acceleration of the spacecraft. Okay, now I'm going to park this last equation up a little bit. Okay, and let me point out one more thing. The acceleration of the human, that's just delta v over delta t. All right? So there's no big, and that's just the definition of acceleration. Same thing over here with the spacecraft, delta v subscript s divided by delta t. And you see anything convenient about that last equation? See anything good in here? And handy? And nifty? And what do you see? Yeah, we got an acceleration. Yeah, we started with an acceleration, and that's good. What else do you notice? What do you notice? Delta t's can cancel. Donna, donna, donna. So let's cancel them. All right, and what you get is, let me get this. This one's not animated correctly. Anyways, you get over here, these are supposed to cancel out. Sorry, you guys. M times delta V equals M times delta V and a minus sign in front of it. Okay? And that tells you that there's this quantity called momentum. If it has this formula, mv, then this leftovers after you cancel the delta t's is going to be a change in the momentum. Now, if the mass of the spacecraft doesn't change and the mass of the astronaut doesn't change, then your equation is basically delta P equals, for the human, equals minus delta P for the spacecraft. I'm missing an equation here. This should have another equation and it disappeared. Okay, the equation it should have is delta P subscript H equals minus delta P subscript S. The change in momentum, Deborah, for the human is opposite in direction but equal in magnitude to the change in momentum for the spacecraft. Okay, so number 3 says momentum exchange between human astronaut and the spacecraft are equal but opposite. Momentum exchange being delta mv. Another way to say it is Newton's third law. This is equivalent to Newton's third law, equal but opposite reaction. All right, now here's my formula. Sorry, it's kind of out of sync. So there it is. And students, as I alluded to last Tuesday and is in the textbook, this is the pair of quantities that are equal but opposite. The forces are equal but opposite. The velocities aren't. Accelerations aren't, but the delta P's are. The changes in the momentum, they are equal but opposite. All right. Now, I'm going to continue on, but let me pause for questions. Just for a second. Question? Question? No? I saw you go like this. Okay. Just stretching. All right, let's keep going. Now, I'm going to introduce a new concept called impulse. And this is just a cool picture from an aircraft carrier. It doesn't really have anything to do with the topic, but impulse. All right, so this quantity that we just put together kind of on a lark, In other words, just by noticing that they're equal, F and delta T's are equal for the skateboarders. That's known as the impulse. Sometimes you see it as F times T. And that equals to delta P. And so here's the equation. And my wonderful students, this is a vector equation. So just like this referee, it points in a particular direction. Okay, the net force and the change in the momentum are always in the same direction. Just as the net force and the acceleration are always in the same direction. And believe it or not, this is the way that Sir Isaac Newton, we believe, considered the third law. He wasn't thinking specifically F equals ma. He was thinking delta P over delta T, which boils down to the same thing. Okay, so the change of momentum is equal to the impulse. And this is yet another version of F equals ma. Now, I have a special homework problem, which I'll assign in about 15 minutes when we dismiss, that involves using this equation F delta T equals delta P. And we're going to try to work out an example of it here in class right now. So let me go to the next screen, and here's what it's going to look like in web courses. A given coin of mass 0.05 kilograms. Here's the text of it. Sliding across the tabletop from left to right. At initial point x1, its speed is 1.7 meters per second, rightward. And then it experiences a frictional force, F equals 0.020 newtons leftward. Question. It slows down to a stop at some position x2, further down the line. What is the stopping time? How long does it take? The way that we figure this out is first by figuring out the momenta and then using the impulse equation with this force. The force in the impulse equation is going to be the friction force. And that is 0.020 newtons to the left, right, in this problem. And we're going to use a minus sign. So make a note of that. And you're going to be doing a calculation and a clicker question in just a minute. So have your calculator and your clicker handy. And as we go through this, it'll help you to have them handy as well. All right, so there's our setup. He starts out at 1.7 meters per second, comes to a stop. His mass, the coin, is 0.05 kilograms. And that's about the right size for a coin, 50 grams. It's subject to a frictional force to the left, 0.020 newtons. Right, so first of all, let's get the momenta. All right, here's the initial momenta, P1. Initial momentum. Mass times velocity. And notice that I have the expression comma rightward. And that is because I have a vector equation here. I'm using that little arrow to symbolize vectorness. And that works out to 0.085 kilogram meters per second. Hey, you guys, a kilogram meter per second is the unit of momentum. It doesn't have a fancy name like Newton, but it is the metric unit of momentum, kilogram meter per second. Newtons are kilogram meter per second squared. This is just kilogram meter per second. Now, momentum number 2 is the easy one. That's 0 because it's stopped. So no matter what the mass is, if it's stopped, its momentum is 0. That allows us to figure out delta P. So here we go. Delta P is just P2 minus P1. All right, now P2 is 0. P1 is 0.085. So I get a negative 0.085 kilogram meters per second here. And now I'm dropping the words leftward and rightward, but I am using a minus sign to signify leftwardness. Question? 1.7? How did I get it? I just dreamed it up. It's an example. I just said, what if? Okay, just a round number I dreamed up. You'll see it again. You'll see 1.7 or 1.8 in the homework, or 2.3 or something. All right, so here's your delta P. All right, now that's going to be part of the impulse equation. The other part of the impulse equation is the frictional force. All right, now that comes in right here. Here's the impulse equation. All right, now this is a vector equation, and remember the frictional force here, right here in the F delta T side of the equation, that's a frictional force, and it's going to be a negative 0.020 newtons. So that's right here in parentheses on the left. Now my delta T, that's what I'm trying to figure out. That's my stopping time. And you're going to figure out a stopping time in a few minutes on iClicker, right, before you dismiss. Question? How did I get this? Because delta P is final minus initial. Okay, so the final is 0, it stopped, and the initial was positive 0.085. Okay, so it gives you a negatory. All right. Now all you got to do is divide both sides by 0.085. If you want, you can cancel. You can cancel here or just keep them there. And I'm going to go to the next page and do some division. Let's do that. Here's that same equation. So you could cancel the minus signs or just leave them around. Here's the impulse equation. Here's your plug-in for the known values. So Aubrey, what you got to do, it's Aubrey, right? Yeah. What you got to do is calculate your delta P kind of off to the side, and then you plug it in right here, okay, which is what we did. All right. And then divide both sides. That'll clear the delta T. And so you have delta T equals a bunch of stuff. Divide by negative 0.020 newtons. Divide by the frictional force, in other words. And there's your computation, which is kind of cinchy. And which works out to delta T equals 4.25 seconds. And probably I think I asked you to round off to the nearest tenth of a second. So there's your stopping time. All right. Now I want to try some calculations with you on the iClicker. Get it ready because we're going to do another question. It's going to be multiple choice, but try to calculate it carefully. Collaborate with your neighbor. Kibitz with your neighbor. Counsel and reason together. And let's do it. All right, so let's try some impulse calculations. And the first one is from outer space. Get my... All right. You observe a large 4.5 kilogram blob of green jello floating in space with speed v equals 2.0 meters per second. Which of the quantities is correct? Okay, so they apply a 12 Newton tractor beam for 2 seconds. All right, see, it's Klingon bird of prey. Seconds. 30 seconds, what? 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, give me a home where the buff. Okay, did everybody get it in? Don't make me sing anymore. All right. 285. Tractor beam of 12 newtons. Delta T of 2 seconds. Donna, donna, donna. Let's see what you guys voted for. Whoa! Woo, doggies. Whoa. All right. Yeah, so if you didn't answer 24, you better make a note of it. Just look for F and the interaction time, the force of the interaction time, if you're trying to figure out the impulse. We're not done yet. We got another question coming. Here it is. Question 3. Now this one is the stopping time. So I'll give you a little bit more time. Now this is just like the coin problem, where we figured out the stopping time of the coin. But instead of 0.02 newtons of friction, you have 11 newtons of hand strength. Melanie, did you get it right? Aren't you clicking? No, I mean the previous one. Did you get the previous one right? Okay, don't let me catch you napping on homework. You're going to have these all over the place in homework this weekend. Do not let me catch you napping. Okay. Thirty seconds. Do you have what it takes? 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Genius time. All right, I'll skip over the derivation. You'll have homework tonight. No, sorry. By lunchtime tomorrow, you'll have homework. Due Tuesday. You're dismissed. 11:44. And we'll do this derivation a little later. Yeah.
Were you doing a test when there was multiple answers on it? Like I had A and B for one, for two different ones.
Well, what you can do is give me your printout. Do you have it? I'll take it and I'll go and look it up. Okay. And I've already done that for one student, two students actually. So, and what do you got? Multiples? Okay. Yeah, well, I'll check it here.
Thank you.
I found an eye clicker like on Tuesday.
Oh my god, that's mine. I was just gonna.
Get out of here.
You guys on your freaking
Oh my god. Okay, I was just gonna.
Is your
come
name
up
on
here
it?
And tell you. No, but this is my code. Okay, so yeah, that's what I was just gonna. I lost my eye clicker today, but I was here in class and I answered the 3 questions, and I was just coming up to you to see if someone found it.
Yeah, but I don't take the papers, but
Is there any way I
missing.
could get credit or something?
No, there's not. But 3 credits is not going to kill you. You you have, remember, 85% is what you need to do, and if this is
These are the first
just
three I've
just don't forget it again, okay? And you'll be all right. You'll still get all of 25 out of 25,
Okay.
okay?
All right. Thank
Because
you.
missing what I'm telling you is missing these three is probably not going to bring you below 85% answer.
Right.
So,
Okay. Thank you.
but you better give her some
Thank you
Skittles or
so much.
something
I literally was
because.
just I went up to Shy and I was like,
Oh, wait a minute! I'm still recording this.